Hello everyone, this is AP Calculus Lecture 5.5b. Logarithmic differentiation is what we call this technique, and it's differentiation where the variable is an exponent. Okay, so the first little bit of info I want to show you is what if you're asked to find y prime of y is equal to x to the x. Okay, so this time the variable is an exponent. Now I want to tell you before we start this process what y prime is not equal to. It's not equal to, you don't use the power rule for this. It's not equal to bring that exponent down front, so x times x to the x minus 1. All right? Do not get caught in that mistake. I've had students do that in the past, so I just want to start the whole lecture off. You do not use the power rule to perform this operation. Okay, so let me outline the steps for logarithmic differentiation. All right, step 1 is take logs of both sides, and we're going to use the natural log since it's easy to take the derivative of. Take logs of both sides and simplify. All right, step 2 is we're going to differentiate implicitly that should ring a bell when we start to do it, with respect to x. And then our third step is solve the equation for dy dx and substitute f of x for each y. Now this last part, step 3, will make sense when I show you how to do it. So we don't want to leave any y's in the answer, so we're going to make a substitution at the very end. All right, so if you need to pause, go ahead, and I'll work a bunch of example problems for you. Okay, so let's make our first example problem the easy one, the one I just talked about. Let's say we have y is equal to x to the x, and we want to find y prime. Okay, step 1, we're going to take the natural log of each side. So we'd have the natural log of y is equal to the natural log of x to the x. Well, the reason that we did that is so now we can bring that variable out in front of natural log of x like a coefficient. So we'd have the natural log of y is equal to x times the natural log of x. And now we can differentiate with respect to x, both sides, d dx. Okay, so the derivative with respect to x for the natural log of y is going to be 1 over y times the derivative of y, which is dy dx. The right side of the equation is a product rule. The first, x, times the derivative of the second, the natural log of x, that's 1 over x, plus the second natural log of x, times the derivative of x, which is just 1, and I won't write that. Okay, so I'd have 1 over y dy dx is equal to x times 1 over x. The x's will cancel and you just have 1 plus the natural log of x. Now let's get rid of this y on the left side, multiply both sides by y. We'd have dy dx is equal to y times 1 plus the natural log of x. Now the people in charge of math do not like you to leave a y in this answer. We know, looking back at the original equation, that y is equal to x to the x. So we're just going to substitute x to the x for this y right down here. So dy dx is equal to x to the x times 1 plus the natural log of x. And that is the answer to this question, not what I wrote down at first, x times x to the x minus 1. All right, pause the video and let's do another one. Okay, our next example is find y prime if y is equal to sine x to the cosine x. All right. So first of all, let's take the natural log of both sides. We'd have the natural log of y is equal to the natural log of sine x to the cosine x. Let's bring that cosine x down front using properties of logarithms. All right, now we're going to take the derivative of both sides. This is our implicit differentiation. All right, so that's natural log of y. The derivative of that is 1 over y dy dx is equal to, okay, another product rule. The first, cosine x times the derivative of the natural log of sine x. So that's going to be times 1 over sine x times the derivative of what we call in my class the blop. So times the derivative of sine x, which is cosine x. You're half done with the product rule. First times the derivative of the second plus the second natural log of sine x times the derivative of the first cosine x. That'd be times negative sine x. So we have 1 over y dy dx is equal to, all right, so we're going to have cosine times cosine. That's cosine squared x over sine x. And then the minus, we've got a minus sign here, so minus sine x natural log of sine x. Okay, so now I'm going to multiply both sides by y. We have y times all that. And then substituting for y, sine x to the cosine x. We've got to go back to the original equation. So dy dx is equal to sine x to the cosine x times all this, cosine squared x over sine x minus sine x natural log of sine x. Okay, so we could multiply this side by sine x over sine x, put this fraction together. I just don't see that that makes things a whole lot better, so we're just going to leave it like this, and that is the derivative of sine x to the cosine x. All right, pretty fancy. Okay, I'll give you a second, pause that. Got two more examples for you. Our next one is from the book. It's number 34 on page 354. We have y is equal to 3 to the 2t over t. So let's take the natural log of both sides. Natural log of y is equal to the natural log of this fraction, 3 to the 2t over t. Okay, let's split all this up here a little bit. So we've got the natural log of y is equal to the natural log of 3 to the 2t minus, okay, using the properties of logs, it's a fraction, so minus the natural log of t. What can I do with that 2t? I can bring it out front. Natural log of y is equal to 2t natural log 3 minus the natural log of t. Okay. Let's take the derivative with respect to x, d dx. All right, when we do that, we would have 1 over y dy dx. All right, and that is, or excuse me, dt. Look at me making a mistake. This is my first video in almost a year. We're going to ddt that thing. My bad. All right, so 1 over y dy dt is equal to. Okay, so this one looks funny. All right, but it's just a t. What would be the derivative of just 2t? Well, the derivative would just be 2, right? Well, 2 and natural log 3, that's just a number that's split apart around that t. You can put 2 times natural log 3 in your calculator and see what it is. It's going to be some decimal number, but that's the same as just a singular coefficient. So when you take the derivative of this, it just looks weird because the natural log 3 part is on the other side of the t. The derivative, is just 2 natural log 3. Okay, the t goes out just like if it were 2t. Then the derivative of the natural log of t would be minus 1 over t. So dy dt is equal to y, multiply both sides by y, times 2 natural log 3 minus 1 over t. Okay, we want to make that y in terms of t to not upset the folk in charge of math. So let's look, what is y? It's 3 to the 2t over t. So let's just write that in. So it looks really nasty. But it really isn't that bad. Now, I could multiply this by t over t, put those fractions together. I just don't think that makes it any better, so we're going to leave it like this. If there is an occasion where we can rewrite a fraction so that something cancels out, we will. But in this case, it's just not helpful. All right, let me give you one more example problem. So if you need to pause, go ahead. We're going to look at example 32. This is one where I do go ahead at the end and make a move to simplify things. So we have y is equal to x times 7 to the minus 3x. Let's take the natural log of both sides. Okay, this is a multiplication here, so I can split those apart. I'm going to give myself a little more room. Natural log of y is equal to the natural log of x plus the natural log of 7 to the minus 3x. can bring that negative 3x out front, and I've got the natural log of y is equal to the natural log of x minus 3x times the natural log of 7. Again, like before, 3 times the natural log of 7 is just a number. Think of both of those as a coefficient out in front of x. Now we're going to take the derivative with respect to x. We have it nice and broken apart using the properties of logs. That's going to be 1 over y dy dx. Ends up the same every time, doesn't it? And that the derivative of the natural log of x would be 1 over x. And the derivative of 3x, natural log 7, the x just goes away, just like in the last example, minus 3 natural log 7. So dy dx is equal to y, multiplying both sides by y, times 1 over x minus 3 natural log 7. Now in this case, well, let's go ahead and plug in here for y. So dy dx, we have x times 7 to the minus 3x. So that's our y value, and now we'll write in 1 over x minus 3 natural log 7. Now what if I multiply, let's see if I can get another color. I haven't used these in a while. I hope this red one works. What if I multiply this side by a clever version of 1? Get that out of the way. X over x. Red pen's not great. I hope you can see it. Ooh. Grabbed the wrong one there. Okay, so then I would have x times 7 to the minus 3x, and then I'd have 1 over x minus 3x natural log 7 over x. Okay, let's move that up to here. So I have x times 7 to the minus 3x times, and we can put this fraction together. We have a common denominator. 1 minus 3x natural log 7 over x. Now the reason I did that was because I have this x out front, and that will cancel with this x here on the bottom. So I end up getting rid of this fraction. So dy dx is equal to 7 to the minus 3x times 1 minus 3x natural log 7. Okay, so I might, on a test, end up stopping, right here at this level. This test is a multiple choice test in my particular classroom. So I might end up stopping right there, or I might take it a step further. So you need to know how to simplify that, just in case. That's why I showed you how to do it. Let me go ahead and give you the homework for this lecture. So pause if you're still writing this example. All right, the homework is on page 354, 29, 30, 31, 33, 35, 45, 46, and 47. 29, 30, 31, 33, 35, 45, 46, 47. Okay? So that is the homework. And you got 4 nice example problems in order to be able to do this. All right, so there's my first video in almost a year. So good luck on this homework, and I'll talk to you next video.